Seventh and final calculus video is optimization, all about optimization. To optimize something means to get the most out of something. So consider if you had a company that made boxes to fit something in. You may want to use as little material for those boxes possible in order to optimize your profit. So therefore you would be interested in a minimum. Or perhaps you have, let's go back to the making boxes, but you want to maximize how much can fit into those boxes, then it's a maximizing idea. So everything to do with optimization is all about either finding a maximum or a minimum, depending on what it is you're trying to optimize. Essentially, it doesn't make a difference of how you're going to solve the problem. But if you see a question and the word maximum or minimum or as much as or biggest or smallest or that kind of number is that kind of word is in the question, then you are probably optimizing, and therefore you will need to find a maximum or a minimum. So some of the things we have to think about is what part of the turning point would give you the maximum or minimum. So we know that our maximum and minimum is like that, but which number is it on the turning point? It's the y value. Notice that the coordinate of the maximum turning point here is 5, 5, but it's this 5. It's the y value that is important, and the minimum, it is negative 5. So now we know that if we're going to find maximum or minimum, we are going to need to find the y coordinate of the turning point. So the y value of the turning point. And now ask yourself, what part of calculus links us to the turning point? What have you been doing until now to find the turning point? To find a turning point, you would use the derivative, and once it's found, we would make it equal to 0 and solve for x. So we wouldn't find y value straight away. We would find the derivative of the function, make it equal to 0 and solve for x, and then we would find our corresponding y number by substituting that x value back into the function we're interested in. I do hope by now that you're listening and thinking, gosh, I do know that already. Just a reminder, why do we make the derivative equal to 0 to solve? Because the tangent line at the points where you have a maximum or a minimum is always a horizontal line, and therefore the gradient is always 0. So don't forget why you keep making the derivative equal to 0. So we need to find the y coordinate of the turning point. We are going to do that by finding the derivative of a function. And once we know the derivative of the function, we make it equal to 0. And then we'll solve for x. And once we've found x, we can sub x back into the function that we may be dealing with. And we will find the corresponding y value, so therefore we'll get what we need. So there is your summary. To find the maximum or minimum, we differentiate the function, we make it equal to 0 and solve for x, sub the x back in to find the corresponding y value, and that value will give us our maximum or our minimum. So this is not quite optimization yet, but I just thought we should quickly do two examples of just recapping how to find maximum and minimum. So for the first one, we've got the function x, so we're going to find the derivative of that function. We make it equal to 0, solve for x, sub that back into the function to find the corresponding y value would then be negative 11. So because that is a positive, our function is going that way, and therefore y equals negative 11 represents the minimum of this function. For the second one, find our derivative. Make it equal to 0. Solve for x. Once you have the x value, substitute that back into the function to to find the corresponding y value, which in this case is 4. This is a negative quadratic, so it looks like that. So what you have found, the maximum value of this quadratic is 4. Right, so now let's move on to the actual optimization type questions. First, I'm going to show you the general steps we should use to cover any optimization question. It would depend on the way the question is worded, and it would depend on how much information they give you in the beginning, but these 8 steps, and you shouldn't learn them off by heart by any means, but at the moment they just give you practice in what you should be doing. So let's just quickly read through them before we actually use them in an example. So number 1, ensure you're clear on what needs to be optimized. So the question might want you to optimize surface area or optimize volume or something. So you have to know clearly in your mind what needs to be optimized. If there isn't a sketch, it's sometimes a good idea to make one. And then you need to set up your optimization equation. So basically it's the formula for what you're trying to optimize from what you saw in number 1. Sometimes there are things called constraints. We will talk about that as we go through the example. But if they've given you some kind of constraint, then you need to make an equation of that one. Solve the constraint equation for one variable only and put it into the optimization equation. You'll see later the reason we're doing this. Your optimization equation, the one that I'm asking you to fill in there, might have more than one variable in it. And you can't derive something unless you know which variable to focus on. So that usually comes from being given a constraints equation, solving it for one variable only, so that you can put that into the optimization equation. Then you can easily differentiate, make it equal to 0 and solve. So let's see what I mean by all of those. Hopefully they will make sense once I've done an example where I'll go through each of those steps. So a rectangle has a perimeter of 160 meters. Find the length and width in order for the rectangle to give the maximum possible area. So firstly, the word maximum is your clue in an exam that you're going to be optimizing something. And what is it you are optimizing? Remember, that was number 1 in our statement. What are you trying to optimize? You're optimizing area. You don't have to be writing all this down when you're doing the solution. Some of these are just a thought process. So in your mind, you are saying to yourself, we have to optimize area. And then I did tell you that if there wasn't a diagram, you must maybe make a sketch. So we're talking about a rectangle. If we call that x and that y, because you will have to give it variables, then you've got that. So number 3 says write down the optimization. We want to optimize area, and how do we find area? We multiply length times breadth. As soon as you write down 2 variables in your optimization equation, you know that there must be some constraints, because there has to be another equation to help you focus on one variable only. So our constraints equation in this case is they've told us that the perimeter is 160 meters. And how do we find perimeter of any rectangle? We need 2 of the lengths plus 2 of the breadths. So perimeter is 2x plus 2y is equal to 160. We can simplify this. So point number 5 did tell us to take that equation, and I want to say again, you do not need to be writing all these points down. I'm just writing them down so you can link them back to the information I gave you. You then have to solve for one of the variables so that we can take it back into number 3 where we had 2, and so therefore we couldn't differentiate it, because remember, the whole key is you want to differentiate the thing you are trying to optimize. We can't differentiate x times y. So therefore, we now want to solve for one of the variables from our constraints equation, and the constraint was that the rectangle had a perimeter of a certain size. So we can divide everything by 2, it's a common factor, and then we can get any one by itself here. So let's get y on its own, subtract x from both sides. Now you can go back to your optimization equation, the thing you're trying to optimize, the area. And since y is equal to 80 minus x, we must be able to put that into y's place. So we have x multiplied by 80 minus x. Let's multiply that out because we can't differentiate anything that has brackets. So we have 80x minus x squared. So our job now is to find the derivative of that, make it equal to 0, and solve. So step number 6 is to differentiate. So the derivative is equal to 80 minus 2x. Step number 7. Obviously, I keep wanting to remind you that I'm only putting this in steps to help you. You would obviously just keep on working down your page as you're going. We've differentiated, so now we need to make it equal to 0 and solve for x. And finally, once one variable has been found, our next step, step 8, would be to take that. We remember what the question was originally asked, what is the length and width? We already know what the width has to be, so now we have to put that back into our equation from number 5, this one here. Y is equal to 80 minus x, and we're trying to find out what y is because we've already got x. So y is equal to 80 minus 40. So in fact, to optimize, to get the maximum possible area of a rectangle, you would change that rectangle to actually become a square. It would be 40 by 40. Let's do example 2. You need to make a box that has a square base. The box must have a capacity of 1000 centimeter cubed. So the capacity must be that, and the box must have a square base. Find the dimensions that will minimize the surface area. So we'll go through all those steps again. We want to minimize the surface area. So remember, step 1 is always to be clear in your mind what you are maximizing or minimizing, and in this case it is surface area. So by writing that down, you can be focused on what you need a formula for. You need to find formula of surface area. I did say that you should draw, not the best box I've ever seen, but will do. So you need to draw your box just to get your idea of what you're looking for. Since the base has to be square, let's say that our base would then be x by x. So all we're interested in now is the height or the length, depending which way you're looking, it doesn't really matter, and that can be y. So let's go back to what we are trying to optimize. So that's our drawing, number 2. What we are trying to optimize is the surface area, so I need to write a formula for that now. So surface area, we've got our 2 squares at the bottom and top, or front and back, and one square is x by x, so we have 2 of them. Added to those 4 rectangles, which are all equal because of the square base, they are all x times y, and there's 4 of those. Again, you need to notice at this stage you have more than one variable. Hence, there must have been a constraint to help you change the equation so that you can focus on one only, for one variable only. The constraint was linked to capacity, and capacity is volume. So the volume of this, of that box you've got with the square base, would be length times breadth times height. But our constraint is that it has to be 1000. And we also don't have L's in 1000 centimeter cubed. We also don't have L's and B's and H's. We have an x times y. So our constraints equation is x squared y is equal to 1000. We want to get one of the variables on its own. Y this time seems the much more sensible one, otherwise we'll be dealing with square roots if we try and get x on its own. So we're going to divide both sides by x squared. I'm actually busy on what I call number 5 now, to get the variable on its own. Then we can go back and look at our original formula that we are trying to work with, the expression, and we're going to use this information. So our surface area is going to be 2x squared plus 4x times whatever y is. So notice I've got this y and I'm substituting what this y is. So that is 1,000, x squared. So that's what our formula now looks like. So we're now going to find the derivative of that formula, step 6. Is it ready to find the derivative? No, it is not, because there are variables in the denominator. I am going to simplify as I'm doing this. X goes into itself once and it will cancel out one of those x's. So therefore we have 4 times 1,000 over x. There's still an x variable in the denominator which we cannot have, so we need to use our exponent rules to bring that up, so that's to the power of -1. We need to find the derivative. Remember, this was surface area, so we're now finding the derivative of that. 4x, and a -1 times 4,000 is -4,000. X to the -2. Step number 7, we want to make this equal to 0 and solve for x. I'm just going to make some more space so we can see this a little bit more clearly. Right, we can't solve if we have negative exponents, so we're going to put that variable back in the denominator. Now we try and solve an equation that has fractions in it, so find the LCD, which is x squared, and multiply every term by x squared. X squared times 0 is still 0. And the last term, the x squareds, would have simplified and cancelled each other out. We can take out a common factor of 4. Divide both sides by 4, and we will now have 0 equals x cubed minus 1,000. Add 1,000 to both sides, and cube root. So x is equal to 10. Our final step then is to take that and put it back into our original surface area. Sorry, not the surface area formula. Oh, sorry, not that one yet. We need to go back to where we had what y was equal to from our optimization formula. Y was equal to 1,000 over x squared. We now know what x is, so we can use that to find the corresponding y value. So 1,000 divided by 100 is 10. So this doesn't always happen, I'll show you, but x equals 10 and y equals 10. And remember again what our original instruction was. Well, we've actually found it. Find the dimensions that will minimize the surface area. So it actually has to be a cube rather than a box that just has a square base. Let's look at one more example. And this time you have a diagram. A soft drink can has a volume of 340 centimeter cubed. Remember, capacity is always linked directly to volume, so 340 centimeter cubed happens to hold 340 milliliters. 1 cubic centimeter holds 1 milliliter. It has a height of h and a radius of r, and they have both been put on the diagram for you. Express h in terms of r. Now, what is nice about this one is you don't really have to be thinking through all those 8 steps I had, because they've actually scaffolded it for you. They're leading you to what it is that you need to know. So express h in terms of r. We know that the volume of the can and is found by using pi r squared h. They've, however, told us that the volume is 340. And if it says express h in terms of r, that means get h by itself. So therefore, to get h on its own, we need to divide by pi r squared. And if we do it on one side, we will do it on the other side. So h is equal to 340 divided by pi r squared. So we have got h in terms of r. Number 2, show that the surface area of the can is given by that, what we see there. Remember, when you show that, you cannot use it, but you could use it in number 3 if you didn't manage to show that. Just imagine for yourself it has said, find the surface area of the can. So remember, for surface area of a cylinder, we have the circle here at the bottom and the circle at the top, and we have this curvy part going all the way around. The two circles can be found by saying 2 pi r squared, and the piece going around the edge is 2 pi r h. Remember, that curvy part actually is a rectangle, which we would normally like to have length times breadth, but in the case of a cylinder, the breadth is the height, and the length is actually the circumference. So that's 2 pi r, and that's where 2 pi r times h comes from for that part. Now we need to put that, if h is equal to 340 divided by pi r squared, then we're going to replace h with that. Notice how I make sure the numerators stay in line and that the denominator goes underneath. It just maybe avoid some careless mistakes. So let's now simplify that. First of all, we've got our pi r, simplifying with that pi in one of those r's. And then we've got 2 multiplied by 340 at the top and an r left at the bottom. So all we have to do to show that it looks like the one in the question is use our exponent laws to bring the r into the numerator position. So we now have the surface area formula. So now it says determine the radius of the can that will ensure the surface area is at a minimum. So in order to find minimum or maximum, we need to find I'm doing number 3 now. We need to find the derivative of the function that we've just found. So we have 2 multiplied by 2, so that's 4 pi r. Remember, pi is a constant. A number of people tend to look at it and want to imagine that it's a variable, but pi is a constant, so it's 3.14. Which carries on. It's an irrational number, but it is a constant. And then on the other next term, we've got negative 1 multiplied by 680, and drop the exponent by 1, so r to negative 2. We're going to make this equal to 0 and solve for r, but to do that I want positive exponents. Multiply every term by r squared, now we want to get the r term by itself, so I'm going to add 680 to both sides. Divide both sides by 4 pi. And then cube root both sides. So to get rid of the cube, we're going to cube root there, cube root both sides. So therefore we have r is equal to, and your calculator work will tell you that it's 3,78 centimeters. So that's the final answer. The radius of that can will need to be 3,78 centimeters in order to ensure the surface area is a minimum. So this would be something that the people making the cans would want to do. They want it to hold 340 milliliters, but they want to use as little tin or stainless steel, whatever it is, as possible to make the can. Right, in this section we also have calculus of motion. So this is where rate is involved. There's always something moving. So rate, which is basically speed, is involved in calculus of motion. So in general, you would be given a function of some sort which represents motion. So for example, a ball being hit into the air by a cricket bat, and then they've modelled that and found the function, and you would be looking at the function representing the movement of the ball through the air. So using that function would then be possible to find information regarding the speed and sometimes even acceleration of the object at a point. In order to find speed, we need the derivative function. So when any type of speed is involved, and it doesn't have to be the word speed, it could be the word rate, so that's also like speed, you would then need to find the derivative of that. If you found that, if you were looking for, if we're talking about the ball going up into the air, you're looking for the maximum height, you would find the derivative and make it equal to 0 and solve and so on. Rate of, as I mentioned, rate of change could also be used in place of speed, and also look out for the word velocity. So all of those would be linked to speed, and therefore all of those would be linked to finding the derivative. If acceleration is needed to deal with, then you're going to be finding the second derivative. Let's have a look at an example from a past paper. The number of molecules of a certain drug in the bloodstream, T hours after it has been taken, is represented by the following equation. So as I mentioned, you would be given a function which represents movement of some sort. The movement here is the drug in the bloodstream. T represents hours, and you are shown here that the hours are going from 0 to 10. So the number of hours lies between the values 0 and 10. The first questions in these are usually very straightforward. So this one says, determine the number of molecules of the drug in the bloodstream 3 hours after the drug has been taken. So therefore we're just using the formula they've given us. Time is 3. Straightforward substitution. And if you put that into your calculator, you should get 216. Don't forget what it is you found. Always keep thinking about that. This is the number of molecules of the drug in the bloodstream. So after 3 hours, there were 216 molecules of blood in the system. Okay, number 2. Determine the rate. Remember, rate tells you you will require the derivative of the function. So I'm going back here to look at the original function to find the derivative. Determine the rate at which the number of molecules of the drug in the bloodstream is changing at exactly 2 hours after the drug was taken. So I'm now going to put 2 into the times place. And using your calculator again, you'll find that the answer should be 72. Again, think about what it is you've actually found. We're talking about rate, so this is 72 molecules per hour. So 2 hours after the drug was taken, the movement in the bloodstream was 72 molecules every hour. Let's look at the third and final part. How many hours, so that means we must be solving for T, how many hours after taking the drug will the rate at which the number of molecules of the drug in the bloodstream is changing be at a maximum? So important words here, rate and maximum. We know that to find the maximum, we always need to find the derivative, make it equal to 0 and solve. However, note that the maximum of the rate has been asked, not the maximum of the original function, the maximum of the rate. So let's go back to the rate. This is what we found in the previous question for rate. And we want to find the maximum of that. So therefore, we need to find the second derivative because we are looking for the maximum of the rate. I'm going to make that equal to 0. Add 6t to both sides, divide both sides, and the answer is 1. So the rate, in other words the speed at which these molecules are going through the bloodstream, will be at its maximum after 1 hour. So that brings us to the end of our calculus videos. I do hope they have helped you.